So first of all, I'd like to thank Wei Qing and Wei Zhu for the invitation. It's always a pleasure to come to IMS for always have very nice workshops. So this is a joint work, recent joint work with my current postdoc Jie Shen and former postdoc visitor Jiang Yang at the South University of Science and Technology, and my current postdoc. So this is about gradient flow, and forget about the name for the moment. It's just we are going to talk about how to develop efficient and accurate numerical schemes for gradient flow. So we have heard lots of talks. With gradient flows, of course, the gradient flows can be used to model many different physical problems. So you have the simplest, you start with the heat equation, and we heard a lot about the Alan-Kahn equation, Kahn-Hillier equation, Sun-Fiume, Pitasi, PMP equations, and most importantly, almost all the phase field can be interpreted as a gradient flow. So what is a gradient flow? It's a flow dynamically driven by a free energy. So you have a free energy, and then you let it to have this form where this L here is a positive operator, so that it automatically, this gradient flow, it automatically satisfies a dissipative energy law like this, and you simply take the inner product of this with the variational derivative of free energy with respect to phi. So some simple examples, if you have a heat equation, you take your free energy to be this. You have Alan-Kahn Kahn-Hillier equation, your free energy is this linear part plus a nonlinear potential, which can take different form depending on your situation. Okay, so as I said, you can have this L here can be a different positive definite operator. So you can talk about the gradient flow in L2. This in this case is just L to be the identity, or the gradient flow in H-1, and in this case the L operator is minus Laplacian, and you can even talk about the gradient flow in H-S. Right, for s between 0 and 1, and here, then L equals to minus Laplacian to the power s. So you have a non-local operator in front of it. So let's fix, if we fix the free energy to be this form, to be this form where the nonlinear potential being a double well type of potential, then the gradient flow, everybody knows, the gradient flow in L2 is the Alan-Kahn equation. And in H-1, so in the conserved form, you get the Kahn-Hillier equation. And so this talk is about how to do basically time discretization of gradient flows. So as Charlie did yesterday, we're going to split so we're going to talk about the H-1 gradient flow primarily, because L2 gradient flow is much easier to deal with. If you know how to deal with H-1, the L2 gradient flow is easy to deal with. So we are going to split the fourth order PDE into a coupled second order equation by introducing a new variable W to be the chemical potential, and in this case, so I guess I put particularly a extracted large coefficient in front of it just to represent the stiffness possibly in the nonlinear coefficient. Right? In the phase field model, this would be eta would be the interfacial width, and so prescribed with the Neumann boundary condition or periodic boundary condition for the chemical potential and for phi. So then this, of course, this splitting also give you a discrete energy law, and here this is just the chemical potential. And the goal is to design simple, efficient, and accurate numerical schemes that satisfies a discrete energy law. Okay, so here are some existing approaches for time discretization. So to start with, people have been using fully implicit schemes. And I think one of the very nice fully implicit scheme is by Chandu and Nicolaides, which give you a unconditionally stable numerical scheme, but it's fully implicit, and so you need to have a condition for the unique solvability, and you need to solve a nonlinear equation. Then I guess Xiaobin Feng and Pro did many nice analysis on this type of scheme, so that the error estimates grows only linearly with respect to the small coefficient eta. And I guess one of the very popular scheme is sort of a linearly implicit, and a stabilizer scheme. So because here it's difficult to solve a nonlinear equation at each time step. So there are lots of ways to linearize the equation and adding a stabilized scheme, adding a stabilizing term, so that it can also be unconditionally stable, but with some conditions on the nonlinear potential, which Lipschitz conditions, which are not even satisfied by the double well potential. And then I guess the most popular method is the so-called convex splitting method, and most people attribute this to Iyer, but I guess Charlie and Stilwood in 93 paper already have used this kind of splitting, but I guess they didn't call it convex splitting. So this is like a recipe, right? You have a nonlinear potential, you split them into the difference of two convex functions, and you treat the positive convex function implicitly, the negative convex function explicitly, then you automatically get a scheme which is unconditionally stable, uniquely solvable, and its solution is just the minimizer of a convex function. So it has lots of advantages, But the disadvantage being two, if you want to criticize it, one is still nonlinear equation to solve. Two, it is hard to derive second order schemes. First order is automatic, right? It's a recipe. Whatever it is, you just do it splitting like that, you get a first order scheme. But for the second order scheme, it depends. If you have a simple nonlinear potential like double well potential, you can do it. But for a little bit more complex situation, it's very, very hard to design second order schemes. And then there's a very interesting way to think about is the method with Lagrange multipliers. This is by a couple of Spanish mathematicians. And so they introduce an auxiliary variable so that you can have more flexible ways to design your scheme. And so what we're going to do is we would like a scheme which enjoys the following properties, right? You would like your scheme to be at least the second order and maybe even higher. And it only requires the solving decoupled, linear, and a positive definite system with constant coefficient. Even you have a system, even you have a gradient flow with multi-component system, which often happens in material science. You could have hundreds of order parameters, And if you want to try to solve them coupled together, it's getting complicated. And they should be applicable to a large class of gradient flows. And it also should be amenable to error analysis without asking a Lipschitz condition. Right? So most of the error analysis, if you have anything explicit in your treatment of the nonlinear terms, then this condition is often required to get a error analysis. You could get away without this condition, without the Lipschitz condition on the second derivative of the nonlinear functional if you use a fully implicit scheme. Okay, so here comes a sort of ingenious method by my former student Xiaofeng Yang and Qi Wang sitting here. And so the method goes like this. The method is a sort of a extension of the Lagrange multiplier. I mentioned it just in this previous slides, but I did not say how do they do it. So this invariant energy quadratization, and I guess Qi Wang will talk about this in a little bit more detail. So I'm going to briefly talk about the idea. So basically, you have your energy. You write your free energy as the sum of squares. As the sum of squares. So, for example, in the free energy, in the usual free energy, you introduce a auxiliary variable u to be gradient phi, and v equals to square root of f phi plus c0, and you want this to be positive, so you need to assume this nonlinear potential to be bounded from below, which is often true, but not always true. And so when this is true, then you can write your functional in the sum of the squares. The constant doesn't matter, right? So once you have the form in the constant of squares, so this is called quadratization, right? Energy quadratization. Then you rewrite your original gradient flow like this. The first one doesn't change. The second one, you take your variational derivative with respect to phi. From here, you get this term, and from here, you get 2v delta v delta phi. And then you need two equations. You need two equations for the extra auxiliary variable u and v. You take the partial derivative with respect to t of v and u. You get those two extra conditions, which are exactly the same as the original equation, but when you try to design numerical schemes, then you have flexibility. Most importantly, the flexibility is here. You can linearize the scheme. For example, here you can treat one part implicitly and the nonlinear part explicitly, right? So when you discretize it, then you have your choice. Its flexibility comes out, right? You can deal with implicitly and explicitly here. So this is now a linearized scheme, and here you also deal with it explicitly. The rest is just standard, right? The linear term is all implicit. And the nice thing about this is no matter what is your nonlinear functional, you always get unconditional energy stability. Why? Because you multiply this by W, you multiply this second equation by this term, and you multiply the third equation by Vn plus 1, which is constant 2. And you see, no matter what is this term here, it doesn't matter what is the form. Those two terms will cancel out. So it applies to anything, right? You have your nonlinear term applies to anything. It's always unconditional stable. But it's with respect to a modified energy, not the original energy anymore. But nevertheless, with this modified energy, it's unconditionally stable with some extra dissipations introduced by the time discretization. Right? Okay, very nice. And so the main advantage of this approach is It's very efficient because it's linear and flexible. It applies to anything almost. And in practice, you can actually eliminate V and U bar and W to just form, get a fourth order equation for phi, but with variable coefficient and positive definite. So it's sort of not so hard to solve. And a more interesting thing is not only you can do first order, it automatically extends to BDF 2 or BDF k. And certainly it allows to deal with a large class of gradient flows. So in the last 2 years, so they were able to use this approach to deal with many gradient flows which were hard to design numerical scheme on. So they were always able to come out with unconditional second order energy stable schemes. So it's been very successful. Okay. But if you would like to be a little bit more demanding, then you say, okay, I still would like to something more. For example, I do not want to solve problems with complicated variable coefficients. And this is very important for people doing finite difference, for people doing spectral methods. To deal with the variable coefficient, it's sort of annoying. And the second thing is sometimes your free energy density is not bounded from below. But the energy, the integral is bounded from below, right? That is a more desirable assumption. And more importantly, if you have multiple components, you don't want to solve, it will lead to coupled systems, and all coupled becomes a little bit more tricky to solve. And so the question is, of course, can we do better? And so the answer is yes for some cases. So for large class of cases, if your free energy takes this form, you can split your free energy into two parts. One linear part, which have the highest derivative term, and a nonlinear part, which include only lower order nonlinear terms. If you have your energy, free energy can be split into this, then you can solve all those problems. Okay, let's see how do we do it. So this is we call the SAV, scalar auxiliary variable. Okay, the main difference here is now I'm going to integrate the function f, and this part of energy, which I call E1, and I will assume this is to be bounded from below. So this is a very mild assumption, which is satisfied almost by everything. And then you introduce one scalar auxiliary variable, R. So your x is integrated out. You only have a scalar function with respect to t to be the square root of E1 phi plus C0. And then you rewrite your equation like this. The first equation never changes. The second equation, the chemical potential equals to minus Laplace phi plus f prime phi, right? And then you multiply it by 1. You multiply by r divided by itself, by 1. And you take the time derivative with respect to t, and you get this equation, right? You take the time derivative with respect to t, you get this, and then you take divide dt, you get this. Okay, this system is equivalent to the previous, equivalent to the original system. And of course, the trick is at the discrete level. So at the discrete level, this is the same. Here, you only, just like in the IEQ, you deal with Rn plus 1 implicitly, and the rest of the term just explicitly. And here also, the nonlinear terms, anything involved the nonlinear term, you deal with explicitly. And And it's easy to see that if you multiply this by W plus 1, multiply the second equation by this, and multiply the third equation by 2Rn plus 1, and then this term and this term cancels out. Cancels out. No matter what is the form of the nonlinear functional, you get the unconditional energy stable with a modified energy like this, with a modified energy. Here, it's not the nonlinear function anymore. It's this auxiliary variable, Rn plus 1 to the square. Okay, so what is the difference between this? What is the difference between this and IEQ? The main difference being that R is a number. Rn plus 1 is a number. And now, how do we solve this? How do we solve this? You write this as you write this coupled system of linear equations in a matrix form. In a matrix form, phi WR. R is a number, and the coefficient for phi and W are constant coefficients. And then you see that you can just eliminate R by doing a block Gaussian elimination, right? So which means you only need to solve this equation once to get R. And once you get R, you solve this equation another times, you get phi and W. So you solve two coupled second order system like this. Linear constant coefficient. And this thing, even under Neumann condition for phi and W, they can be further reduced to a set of decoupled equations. So you can find a psi, which is a linear combination of phi and Laplace phi, or psi equals to this. For suitable alpha and beta, you can determine alpha and beta such that you first solve this equation. Solve this equation with d psi dn equals to 0. And then once you have psi, you solve another Poisson type equation for phi. So at the end of the day, you only solve Laplace equations. You only solve Poisson type equations. Yes.
So the coefficients alpha, beta are all positive?
Yes. Yes.
Otherwise, you have a couple.
That's right. Alpha, beta are. Okay, so this is extremely easy to solve. And now, how do we do second order scheme? You do second order scheme very easy as well. You just, there are different ways to do it. You, for example, take PDF2, and here's a nonlinear term. You do the Adam-Bush force extrapolation. And time derivative, you do PDF2, and immediately, the same way as before, you multiply this by Wn plus 1, you multiply this by this PDF2, and you multiply the third by Rn plus 1, and you have this to be unconditionally energy stable again, right? You can even apply this to BDFK for k equals 3, 4, 5, 6. It give you 3, 4, 5, 6 order schemes, but since they are not astable, you do not really have unconditional energy stable in theory, but in practice, it's almost always, even for third order, fourth order, it's numerically it's almost unconditional energy stable. Okay, so here are the main advantages, which I'm going to repeat again. So up to second order unconditionally stable and can be extended to higher order. It only requires solving decoupled linear second order equations with constant coefficient. So extremely easy to solve. And it only requires the integral of the this nonlinear energy density to be bounded from below. So it sort of applies to a larger class of gradient flow in this context. So next time, later we're going to show how to do this with multiple components. With multiple components, no matter how many components, you can decouple them. You can decouple them and still to be unconditional stable. So this is the essence of this approach. And so now I'm just going to show you some numerical results, show you some error analysis, and depending on how many time I have, I will show you some of the applications to different kind of situations. So the key message to take away it is if you have your free energy can be decomposed into one linear part plus the rest, and the linear part includes the highest derivative terms, then you can apply this SAV approach. It's a recipe, right? It's a recipe. It does not require any other assumptions or any techniques. It's a recipe. Okay, so those are some examples to check the accuracy. So this is just an example for Alan-Kahn equation, a ball which shrinks with time, and we know the velocity of shrinking, and you get the perfect second order accuracy, and with very reasonable time step. That t equals to 0.1, you can distinguish it from the exact solution.
It is conditional stable.
No, unconditional stable. It is the key is unconditional stable, and so it is unconditional stable with a modified energy, right? But what about the original? You are interested in the original energy, and of course we cannot. We were unable to prove the unconditional energy dissipation for the original energy, but numerically, the original energy decays. It decays monotonically with time. So even though we cannot prove it, and so this is a test for third order equations. For fourth order schemes, third order schemes they give perfect fourth order and third order, and you can do it with very large time steps. And okay, so here's I guess an important point. So why you might want to say, why do I need unconditionally energy stable schemes? If I have some conditional stable scheme, they can do as well. The unconditional energy stable scheme, the main advantage is that you can couple it with an adaptive time step, right? You look at the energy curve. You look at the energy curve or the previous energy curve like this, whatever. You see most of the part, they change very little, but at some place they will have very large variations. So if you use a conditional stable scheme, you are restricted by the smallest time step constraint, which you have to keep all the time, right? You cannot change. For the accuracy, yeah. For the accuracy, no. I mean, not for the accuracy. If you have a conditional scheme, you are required by the stability of your scheme. That's why I say yes. That's why the unconditional scheme, then you can adjust your time step based on accuracy. Right? Here you can do very large time step, and here you do small time step. So it's only restricted by accuracy. So for example, and so here is the original energy, here's a modified energy, and this blue line is with a large time step, so that it's not very accurate. And if you use adaptive and smaller time step, then you get the perfect agreement. So here's the original energy, modified energy, the same story. And here are the time step from time t equals to 0 to 1. You see that you start with a time step to be 10 to the minus 5. You gradually can increase your time step to a couple of hundreds larger, right? So it includes this. So adaptive time stepping is really the way to maximize the efficiency of your scheme. And okay, I'm not going to talk about it. This is just you use adaptive and the small time step, you get good results. If you use a larger time step, then your results are not accurate. Okay, so I will mention a little bit about the convergence and the error analysis. So as I said, the SAV schemes are semi-implicit schemes. When you linearize your nonlinear term, and when you try to do the error analysis, you normally have to require your nonlinear terms satisfy certain type of uniform Lipschitz condition. Uniform Lipschitz condition. And unfortunately, this uniform Lipschitz condition is not even satisfied by the double well potential. And then you have to make some assumption, say that, okay, my nonlinear free, the double well potential, I am only interested in phi to be bounded, right? The other far away is not very important. So you have to make this kind of argument. And but here, because the scheme, we have the scheme which is unconditionally energy stable without any condition on the free energy. So this allows us to derive H2 bonds for the numerical solution under very mild conditions of the free energy. And once you have the H2 bonds, you have L infinity bonds. And so why do they need a Lipschitz condition? Is they cannot have L infinity bonds, so they require that. And then everything else just comes naturally with error estimates. So basically, you have this kind of results. We cannot do it for very general nonlinear potentials, but we can do it for at least for polynomial type nonlinear potentials. And so for polynomial type nonlinear potentials, you can have the H2 bonds. You can have H2 bonds, uniform H2 bonds, and once you have the uniform H2 bonds, and then you have everything else. So here you see that so for 1 dimension, 2 dimension, the polynomial degree can be any order, and for the 3 dimension, the polynomial degree has some restrictions, but it covers at least the double well potential. Okay, once you have that, then you can prove that you can prove convergence. So you have your discrete value at time step n, and you can make up a time-dependent function by piecewise linear or piecewise constant functions, and then you can prove those made-up functions will converge to your exact solution in quite strong norms, which I'm not going to focus on. And once you, for the convergence result, you basically do not need any assumption, just the previous assumption on the nonlinear potential polynomial type. Then you have the convergence. And if you would like to have error estimates, and of course you need some smoothness assumption. And here, if you have some smoothness assumption, then you can prove the convergence result. So those are once you have the H2 bond and the convergence, this is pretty standard. So we did the example for the first order. You can do it for the second order with some extra smoothness assumption. Okay, so now we're going to talk about several applications. And one is the MBE, which was mentioned in this workshop. So here we look at the MBE without slope selection. With slope selection, it's much easier to deal with. And the problem without slope selection is this part of the nonlinear term is not bounded from below. So now once you don't have that sign, the recipe does not apply. So you have to do something. And so this part It's not bounded from below, but you can show that if you borrow a little bit from the linear term, just a little bit for any alpha bigger than 0, then the energy will be bounded from below. Then the energy will be bounded below. Then, which means you can apply the SAV approach. Once you have that, it's a recipe. You just apply it, and you get you write your. Okay, so you just introduce a RT to be this part, and you split the energy function to be this part plus this part, right? This part you deal with implicitly, and this part you deal with explicitly in a numerical scheme. And here, so you can, here is an example. You do it with a Kronecker-Nicholson type. So with the Kronecker-Nicholson type, you do also this extrapolation, right? The nonlinear terms you do extrapolation. Nonlinear terms do extrapolation. Everything else is just Kronecker-Nicholson, and so the scheme also is unconditional, energy stable, etc., etc. So here are some typical cosaning results, and the cosaning rate, which matches with the expected log rate, etc. Here's a vesicle membrane model that Charlie mentioned yesterday, and here we only deal with the bending energy without the line energy. With line energy, a little bit more complicated. So you have this bending energy, and you have this volume and the surface area constraint. You want the volume and the surface area to be conserved. So to deal with this, you can have two ways. One is like Charlie did with Lagrange multiplier. Another way to do it is you can do it with a penalty, right? You add a small parameter gamma eta here to penalize this those two terms, and so this is your total free energy, and so your task to apply the recipe is you have to split this energy into two parts, right? Split this energy into two parts. So to split this energy into two parts, you have to look at the bending energy. So bending energy, you expand them out, so you get two linear terms and the two nonlinear terms. And the linear terms, you put it into implicit part, and this part, along with the volume and the surface area constraint, you deal with this by introducing SAV. So this is the recipe, right? You do it like this. And unfortunately for this problem, this SAV approach does not really, it works, but it does not work as well as expected. The problem is you have this gamma and the eta, which can be very small, and so those terms, they behave very differently. So they dictate actually a quite small time step to make the simulation accurate. So for that, we introduce, we realize that maybe one SAV is not enough. You have to do it with a couple of SAVs. And here you see that then, if you look carefully, this is a linear term. A phi is just phi, or phi plus 1. So this is a linear term which we can include in this part, in the implicit part. So we are not going to deal with this part here. So we are going to deal with this part by introducing another SAV. So I have two SAV now. One is U, one is V. V now only includes the part from the bending energy. You don't want too many small parameters in one SAV. And then the total energy can be represented by the linear part here plus the nonlinear part. So this is sort of like IEQ. So this is a combination of IEQ with SAV, with multiple. Now you have multiple SAV now. And then you write your L2 gradient flow just like this. Here's a mobility. And then mu is a chemical potential with respect to phi. And you need extra equation for U and the extra equation for V. And this is the recipe again. So so here's a second order scheme based on Kronecker-Nicholson. And mu n plus half is just half of mu n plus 1 plus mu n, right? The Kronecker-Nicholson approximation. And the key is the star n plus half is the extrapolation. So you do this with the extrapolation. And here, okay, here why do I do this with the extrapolation? So even though this is a linear term, this is a linear term with a bad sign. So this is a linear term with a bad sign. It's no good to deal with it with implicitly. With a bad sign, you better do it explicitly. And here's this. And then with the two SAV, I deal with U and V implicitly, and the nonlinear term, of course, explicitly. And then you have two equations for U and V. So this is exactly the same way as with one SAV, except you do this explicitly because this one does not have good signs.
So your delta squared is Laplacian or
Biharmonic.
harmonic?
Delta square, where do I have delta square? Oh yeah, it's biharmonic.
The biharmonic is not so easy to solve, right?
It is. Biharmonic, I showed you, biharmonic can be decoupled into two, yeah, two percent. For me, biharmonic is very easy to solve. If I do it with the spectral method on the square domain, I don't care biharmonic or whatever. Huh?
Depends on the boundary condition.
Of course, depends on the boundary. Here, the natural boundary condition is just the Neumann boundary condition. Right? Okay, so now instead of one, you have two. But remember, those two variables are still scalars. So you can eliminate them just like using one variable. And then you have to solve, they are coupled together. You solve a 2 by 2 algebraic system. So basically, the cost is just like solving the equation with one SAV. And you have energy stability and so forth. And here are just some example without the volume and the surface area constraint. And here's an example with volume and the surface area constraint. So it will evolve into different shape, and in this case, a donut shape. Okay, maybe I talk a little bit about a gradient flow with multiple components. So if you have lots of components, k components, with a linear term and a nonlinear term like this, then you do the same. You just need to introduce one scalar variable, one SAV RT equals to square root of this, and then you take the gradient flow. So you have for each phi I, you have one equation, right? For each, then you have one equation. Everything is coupled together here. Everything is coupled together here. After you introduce this R, it's coupled by R. Where did I go? Yeah. Oh. No. And then you just discretize that SAV formulation, right? Like before, everything nonlinear explicit, linear implicit, and then this is unconditional stable, easy. And how do you solve it? How do you solve it? You see, everything is coupled just by this. If R, n plus 1 is known, then you just need to solve each equation separately. So which means you can eliminate R by solving a decoupled system like this. And once you solve the R, you can solve phi. So basically, you just solve one by one, solve them one by one. And so here's just, we started to, I taught this with my longtime collaborator, Longqing Chen at Penn State. So he's interested in doing this with many components. And here's an example with 100 grand growth with 100 components. And you can solve it very, very, very fast. And okay, I guess I don't have time for this thing. Why only have that? And you can do this with two-phase incompressible flows. And I'm going to skip that and conclude with a few remarks. And I guess I'm going to stop here. Okay, thank you. So if you are interested, so here are a couple of papers related to the talk. So the method is presented in this paper, and we wrote a paper submitted to SAM review with lots of examples, and the convergence and error analysis is submitted to SAM. Oh, okay.
But not the graph, the results. So there was an interesting talk I attended some time ago by Jie Shen, explaining that this splitting method, the semi-implicit splitting.
I know his talk.
The result is identical to the explicit method, except time is.
No, he has a reason for it, but only for the first order scheme. The second order scheme is not like that. First order scheme, you have large splitting error, which means it is only a time delay, but not for the second order scheme.
So my question was that if you wait long enough for that result that you showed, this one, right, the last one.
Yeah.
Next slide. The one. If you wait long enough, would you get to those?
Oh yes, if you are interested only in equilibrium. If you are only interested in equilibrium, of course, everything goes to the equilibrium. But if you are also interested in the transient, then that's a different story, right? If you are just interested in the equilibrium, you can do anything. You don't have to deal with the high order schemes, right?
You said the Laplace, solving the Laplace equations for phi and psi. I mean, can you just simply use any method like multi-grid or?
That's right. You can use anything. So no, I forgot to say, right? I only presented in the time discrete form, but you see my test function. My test function is all simple test functions. You can apply to any method. Finite element spectral method for finite difference as well. You can apply to any method. So the spatial discretization, it's very flexible. You do anything you want.
What about non-smooth free energies like an obstacle?
That's a little non-smooth. You can still so most people do regularize it, add something to regularize it. You can still apply, but then of course the convergence and error estimate theory needs to be modified, right?
But you think practically?
Practically, it depends on how you would like to smooth it. We tried with this image processing, the L1 grid, the L1 millimeters. Yeah, you regularize it, then you are fine. You can still do it.